Welcome back to the first PUC topic. We were studying the topic on hydrogen spectrum, atomic structure. In that one we were studying this Bohr's model. So in this Bohr's model, along with this Bohr's model, we have studied the limitations. There are so many limitations for this Bohr's model. The first one is the limitations. What we have studied in the earlier class are it does not explain multi-electron atoms. So we consider only hydrogen atom or hydrogen-like species to explain the Bohr's model. The second one is it does not explain fine spectrum. Does not explain fine spectrum. This is fine spectrum when we consider the hydrogen spectrum in presence of an electric field. So in presence of electric field, it splits into the fine spectrum, that is called as the Stark effect. And in presence of the magnetic field, we consider this as the Zeeman effect. So individual lines in the various regions of the hydrogen spectrum, ultraviolet, visible, IR, etc. we consider the single lines, Lyman series, Balmer series, etc. But each such individual line will split into the group of lines in presence of the electric field. That splitting is called as the Stark effect. In presence of the magnetic field, it is called as the Zeeman effect. These two cannot be explained by the Bohr model. The third one is it does not explain the dual nature of the electron. So when we consider this particle nature, electron is considered as a particle with a certain mass, 9.1 into 10 to the power minus 31 kg. So it is considering only particle nature in case of this Bohr's model. But we have this electron behaving as a wave as well as a particle, that is dual nature. This is actually explained by de-Broglie's hypothesis. And also we have this uncertainty principle. This is actually explained by the Heisenberg. So to explain this dual nature of electron, we consider the de-Broglie's hypothesis, and also to explain the uncertainty, we consider this Heisenberg's uncertainty principle. So let us consider these two now. When we consider this dual nature of electron, we have this Lewis de-Broglie hypothesis. If you consider this electron energy, according to Einstein's equation, we have this E is equal to mc square. But we know that E is also equal to h nu, that is also equal to hc by lambda. Since energy of various substances, photons, can be calculated by using the Einstein's equation, E is equal to mc square. And for an electron, we have this E is equal to h nu or E is equal to hc by lambda. Equating these two equations, we have this mc square is equal to hc by lambda. Therefore, lambda is equal to, just bring this mc square to the other side, we have this hc divided by mc square. One of the c gets cancelled. Therefore, lambda is equal to h over mc. For other particles, we write this as h over mv. For electron, we write this electron velocity c. For any other particle having the lower mass, we can consider the velocity is equal to v. Here lambda is wavelength of the electron, h is Planck's constant, m is mass of the electron, and v is velocity of the electron or velocity of the particle having very, very low mass. So for any such particle having the very low mass, we can calculate the lambda. So this equation is called lambda h over mv is called de-Broglie's equation. That means according to this de-Broglie, electron not only behaves as a particle, it also behaves as a wave. So for any particle, any material having a wave character, we can calculate the lambda. For any particle, we have this mass. So both particle nature as well as the wave character are included in this equation. So this equation is called as de-Broglie's equation. De-Broglie's equation. For any particle whose mass is known, velocity is known, we can calculate the lambda. That is wavelength of that particular particle. Let us take one or two examples for this. That is for de-Broglie's hypothesis. Suppose you are having a particle moving, having a mass is equal to 10 to the power minus 4 kg. Mass is equal to 10 to the power minus 4 kg. And let us say velocity of that moving object is with 100 meter per second. If it is moving with a velocity of 100 meter per second, then we can calculate the lambda for such a particle. So here lambda is equal to h over mv. H is equal to 6.626 into 10 to the power minus 34. This is actually joule second. Divided by mass is 10 to the power minus 4 kg into 100, that is meter per second. So if you simplify this, in the denominator we will be having 10 to the power minus 2. Therefore, the lambda for such a particle 6.626 into 10 to the power minus 32. This is actually expressed in terms of meter. Now let us calculate the lambda for the electron itself. Suppose the velocity of the electron is equal to 3.3 into 10 to the power minus 4 meter per second. Actually it is, we can write this as 3 into 10 to the power minus 8 meter per second for electron. Now let us consider the mass of the electron, 9.1 into 10 to the power minus 31 kg. If you want to calculate the lambda for such a moving electron, we write this as 6.626 into 10 to the power minus 34 divided by 9.1 into 10 to the power minus 31 into 3 into 10 to the power minus 20. 3 into 10 to the power minus 8. All are in SI units, so we can very easily simplify. This is 6.626 into 10 to the power minus 34. In the denominator we have 327.3 into 10 to the power minus 39. So if you simplify this, this will be 6.626 10 to the power minus 34. 10 to the power minus 1 I am taking here. It is 2.7. 3 into 10 to the power minus 38. So if you simplify, this is almost 2.5. It is equal to 2.5 into 10 to the power 4 meters. So the wavelength is very, very large. So we can calculate the wavelength of any such particle whose mass and velocity are known. So this is about one limitation, that is de-Broglie's hypothesis, that we cannot consider, that we cannot explain by considering the Bohr's model. Now let us consider the next one, that is Heisenberg's uncertainty principle. When we consider this uncertainty principle, when a particle is to be observed, certain light has to fall on that particular particle. But we know that electron cannot be easily observed with the naked eye. That's why we have to use some spectroscopic methods to identify the position of the electron. But when light falls on it, its position will change and also velocity will change. So according to this Heisenberg's uncertainty principle, Heisenberg's uncertainty principle, this states that, you can write the statement for this: it is impossible to determine the position as well as the momentum of electron accurately and simultaneously. Accurately and simultaneously. I'll repeat. It is impossible to determine the position as well as the momentum of the electron accurately and simultaneously. So if you determine the position of the electron accurately, there will be uncertainty in the momentum. If you determine the momentum to the more accurate value of this momentum, there will be uncertainty in the position. Assume that delta x is the uncertainty in position. Uncertainty in position. Along x-axis we can say. And delta p is uncertainty in momentum. Uncertainty in momentum. Then, according to this Heisenberg's uncertainty principle, this delta x into delta px either equal to or greater than h over 4 pi, where h is Planck's constant and pi is equal to 3.14. So if you determine this position of the electron accurately, there will be uncertainty in the momentum. If you determine the momentum of the electron accurately, there will be uncertainty in the position. So the minimum value of product of these two, uncertainty in the position and uncertainty in the momentum, will be h over 4 pi. So it may be greater than or equal to h over 4 pi. So delta x is uncertainty in the position, delta px is uncertainty in the momentum. Therefore, we have delta x into delta px is greater than or equal to h over 4 pi. So this is about the Heisenberg's uncertainty principle. That means when we consider the Bohr's model, according to that one there is a circular path around the nucleus where electron is revolving. But since electron behaves as a particle as well as a wave, and also its position cannot be determined accurately, so this orbit concept does not exist. So that is explained by considering the new theory that is called as the modern theory of the structure of the atom, that is called quantum mechanics or quantum model of that structure of the atom. That we shall take up in the next video. Thank you.